Engineering drawings are more than just technical illustrations. They are the language engineers use to communicate their ideas and translate concepts into tangible objects. These detailed graphical representations serve as blueprints for everything from simple components to complex machines. Imagine trying to build a skyscraper with nothing but a rough sketch on a napkin. That's where engineering drawings come in. They provide the precision and clarity needed to transform visions into reality. Think of engineering drawings as the instruction manuals for manufacturing. They provide a universal language that everyone involved in a project can understand, regardless of their native tongue. By adhering to established conventions and symbols, these drawings eliminate ambiguity and ensure that everyone is on the same page. Like any language, engineering drawings have their own grammar and vocabulary. These drawings are the universal language of engineers, allowing them to convey complex ideas and designs with precision and clarity. They are essential tools in the engineering world, bridging the gap between concept and reality. Dimensions, for example, are the precise measurements that dictate the size and position of every feature. They ensure that each component fits perfectly within the larger assembly, maintaining the integrity and functionality of the design. Without accurate dimensions, even the most innovative designs can fail. Views, on the other hand, offer different perspectives of the object, from the front, side, and top, providing a complete three-dimensional understanding. These multiple views help engineers visualize the final product, ensuring that all aspects of the design are considered and optimized. Symbols are another crucial element, acting as shorthand for commonly used features like holes, threads, and welds. These symbols are standardized, meaning that engineers around the world can understand and interpret them without ambiguity. This standardization is key to maintaining consistency and quality across different projects and teams. These standardized symbols eliminate the need for lengthy written descriptions, making the drawings more concise and easier to interpret. By using symbols, engineers can quickly convey complex information, saving time and reducing the risk of miscommunication. Finally, annotations provide additional information that cannot be conveyed through graphics alone. These notes can include specific instructions, clarifications, or additional details that are crucial for the successful implementation of the design. Annotations ensure that nothing is left to interpretation, providing a clear and comprehensive guide for the manufacturing process. This can include surface finish requirements, material specifications, or manufacturing tolerances. These details are vital for ensuring that the final product meets all necessary standards and performs as intended. They provide the final layer of detail that brings the design to life. Together, these elements form a comprehensive language that enables engineers to communicate their designs with clarity and precision. By mastering this language, engineers can ensure that their ideas are accurately translated into reality, leading to successful projects and innovative solutions. Imagine a world where every engineer spoke a different language, using their own unique symbols and conventions. Each blueprint would be a puzzle, each drawing a mystery. Communication would be chaotic, misunderstandings rampant, and the risk of errors astronomical. The simplest task could become a monumental challenge, and collaboration would be nearly impossible. This is precisely why engineering standards are so crucial. They act as a universal language, bridging gaps and ensuring clarity. Standards provide a common set of rules and guidelines that ensure everyone is speaking the same language. They create a foundation upon which complex projects can be built with confidence. They define everything from the way drawings are presented to the meaning of specific symbols and abbreviations. This uniformity is not just about aesthetics, it's about precision and reliability. This uniformity minimizes the risk of misinterpretation, reduces errors, and promotes consistency across projects and teams. It ensures that every engineer, regardless of their background, can understand and contribute effectively. Without standards, the manufacturing process would be fraught with uncertainty. Each step would be a gamble, each decision a potential misstep. Imagine receiving a set of drawings with ambiguous dimensions or conflicting symbols. The confusion would be immediate and the consequences could be severe. Manufacturing would grind to a halt as engineers scramble to decipher the designer's intent, leading to costly delays and potential rework. The entire workflow would be disrupted, causing a ripple effect of inefficiency and frustration. By adhering to established standards, we ensure a smooth, efficient, and error-free process. Standards are the backbone of successful engineering, enabling innovation and progress without the chaos of miscommunication. While the need for standards is universally recognized, the specific standards used can vary depending on geographical location and industry. Standards are essential in ensuring that products and services are safe, reliable, and of good quality. They provide a common language and set of expectations that help to streamline processes and facilitate international trade. Two of the most widely adopted standards are the International Organization for Standardization, or ISO, and the American Society of Mechanical Engineers, or ASME. These organizations have developed comprehensive sets of guidelines that cover a wide range of industries and applications, from manufacturing and construction to information technology and environmental management. ISO standards, as the name suggests, are internationally recognized and widely used in Europe and Asia. They are designed to be applicable across different countries and industries, promoting global interoperability and compatibility. ISO standards are developed through a consensus process involving experts from around the world, ensuring that they reflect the latest technological advancements and best practices. ASME standards, on the other hand, are predominantly used in North America. They are particularly well known in the fields of mechanical engineering and pressure vessel design. ASME standards are developed by committees of industry professionals and are regularly updated to incorporate new research findings and technological innovations. While both standards share the same goal of ensuring clarity and consistency, they differ in some key aspects. These differences can affect everything from the way drawings are interpreted to the materials and methods used in manufacturing. Understanding these differences is crucial for engineers and designers who work on international projects or collaborate with colleagues from different regions. One of the most notable differences lies in their projection methods. Projection methods are used to represent three-dimensional objects on two-dimensional surfaces, such as engineering drawings. The choice of projection method can influence how easily a drawing can be understood and interpreted. ISO standards typically employ the first angle projection, where the object is projected onto the plane of projection as if it were casting a shadow. This method is commonly used in Europe and Asia, and is often preferred for its straightforward representation of objects. ASME standards, conversely, use the third angle projection, where the object is projected onto the plane as if it were being pressed against it. This method is widely used in North America, and is favored for its intuitive layout, which aligns with the way objects are typically viewed in real life. Another key difference lies in the units of measurement. The choice of measurement units can have a significant impact on the design and manufacturing process, affecting everything from material selection to quality control. ISO standards primarily use the metric system, which is based on units such as meters, kilograms, and liters. The metric system is used by most countries around the world, and is known for its simplicity and ease of conversion. ASME standards traditionally use the imperial system, which is based on units such as inches, pounds, and gallons. The imperial system is still widely used in the United States and some other countries, particularly in certain industries. These differences, though seemingly minor, can have significant implications in manufacturing, highlighting the importance of understanding and applying the correct standard for each project. For example, using the wrong projection method or measurement units can lead to errors in design and production, resulting in costly delays and rework. By being aware of the differences between ISO and ASME standards, engineers and designers can ensure that their work meets the required specifications and is compatible with international standards.